So again, it's an honor being here. My work is mostly on like a differentially private algorithm design, and I'll talk today about kind of like several papers in this topic. And so this is going to be a kind of overview of some topics rather than like an in-depth on one paper. And of course, if you have any questions and want to like discuss, please do. So great. What do we actually mean when we talk about online learning? So we might think about like answering queries on some database. And so, for example, here we have a scientist who wants to kind of like access data through some queries, get back answers, ask a new query, get back a new answer, and eventually she wants to output some hypothesis that is like consistent with the data. We may also be thinking about cases where she wants to like produce synthetic data. And so the goal here is going to be through the same process back and forth, rather than outputting some like hypothesis, output a brand new database. And it may be slightly different, as illustrated by the colors. It may be smaller. But this is like a particularly important when companies want to collaborate with like external researchers. It's much easier if they just like hand them data. But for obvious legal reasons, we don't want to just hand over the exact data, but instead you might want some kind of like privacy preserving barrier, right? Either between the analyst and the data, or perhaps between the analyst and the outside world, depending on where the trust lies. And so these are the two things to kind of like keep in mind as we're going through this talk. And the question is then, what does this privacy preserving barrier look like? And like in the privacy space, everyone has their favorite story of like privacy gone wrong. And this is my favorite story. So back in 2006, AOL, who like back then was a major internet company, they were trying to do something nice for the research community, and they published anonymized versions of about like 20% of their users' search histories. And they said they were going to make it anonymous, and they kind of like removed everyone's name and they gave them random IDs. But if you think about things that you search for, you probably search for restaurants in your neighborhood, topics related to your courses at the university. You might search for like papers that you're working on, or you might even search for like your own name. And that's what's happened here. She searched for like services in her neighborhood, people who had her same last name, and then also homes sold in a very specific like a geographical region. And it wasn't very, very hard for some like New York Times reporters to find out who this like person was. And she also searched for some perhaps more embarrassing things, like some, medical conditions, elderly dating sites, and dog that pees on things. And so she probably felt that her privacy was not very preserved in this process. And in fact, here is her dog, who is apparently guilty of like peeing on things. And so this kind of brings up the question, how do we anonymize data? And the answer is we don't. And the famous privacy theorist, Cynthia Dwork, who is faculty at Harvard, famously says de-identified data isn't, meaning that either it's not properly de-identified, as in this case, or it may be that if we take out so much of the content to make it anonymous, it's no longer data, right? And so back to the example of your own search histories. If we take out anything related to like Sharif, Iran, your neighborhood, your family, your hobbies, well, there's no longer really any data there to be left with. And the wrong response here is to give up and not use data. I think these days, as we are more in the big data, machine learning age, companies and people understand data are a valuable resource. We shouldn't give up on them. But especially like in the early days of privacy concerns, companies would really do this. And so this is a Scientific American article that said, quote, as awareness of these privacy concerns has grown, many organizations have clamped down on their sensitive data, uncertain about what, if anything, they can release. And especially in the US, where kind of everyone sues everyone, you really didn't want to release data if you couldn't guarantee privacy of it because you risked having a lawsuit. And so now let's take this more like an intellectual academic approach to like privacy. If we agree privacy as an abstract concept is important, how do we formalize that into something that we can make mathematical? And like in this talk, we're going to like take like the approach. Privacy is about promising people freedom from harm. And so here we would like to say nothing bad is going to happen to you because you share data with some analysis. You're not going to have reporters coming to your door asking about your search history because you share data online. And more precisely, we're going to say some analysis of a data set is private if the analyst knows almost no more about Alice after the analysis than he would have known had he conducted the same analysis on the same database, but just with Alice's data removed. And so we're basically comparing two like counterfactual worlds. One is the real world, and one is like the world that is the same except for one person's data. And we're saying if I can learn the same thing on these two separate databases, I'm not learning about Alice specifically, but I'm learning about the population to which Alice happens to like belong. And it's important that we say precisely almost no more about Alice, because if I said I know like nothing about Alice, well, like, you know, there's an example, there's a causal link between smoking and lung cancer. I have now learned that if Alice smokes, then she is more likely to have lung cancer. And that's the kind of things that we want to learn through these analyses. But I'm also not learning about Alice specifically as an individual. And so that's kind of the nuance here, how we're trying to learn from the population, but not learn about the individual. And this was defined back in like 2006, and this is differential privacy, which was introduced by Dwork, McSherry, and Seaman Smith. And then pictures, it says this: take your data set and plug it into your favorite randomized algorithm. And it's important that this is a randomized algorithm, and this will produce a PDF of the outputs. And so here on this x-axis, we're going to have all possible things that may be produced by this algorithm. And then like on this y-axis, I'm showing what is the probability that I produce this thing as a result of running this algorithm on this particular data set. And so this is basically like a PDF of the outcomes of this algorithm instantiated on this particular data set. And I want to think about some counterfactual world where I change Alice to be Javier, and I then plug this database that is like the same except for one person into my same algorithm, and I'm going to get out a slightly different curve. And the goal is going to be that these curves are close in some sense, and they're not going to be too different after changing one person's data. And precisely, we're going to talk about this ratio being like a bounded pointwise between these two curves. And this is like an important privacy notion, because then I can say if the output of this algorithm truly was the element corresponding to this line, no one could make inferences whether this output came like because of Alice or because of Javier, because these two things would be produced with about the same probability, regardless of which person's data I saw. And so effectively, we're going to bound the kind of like a maximum amount the one person's data can change the result of some analysis. Formally in math, we say that some algorithm M that maps from like an n tuple of types. And so think of this as being like data coming from n people into some arbitrary output range R is going to be parameterized epsilon delta differentially private if it is the case that like for all neighboring databases that are the same except for one person's data. And so again, think of changing Alice into Javier between these two. And for all possible things that may be produced as a result of this output, I'm going to produce that thing with about the same probability under these two neighboring databases if I plug them both into the same algorithm. And this notion of like about the same has two parameters. The first is this e to the epsilon term, and so this is effectively bounding the ratio of these two terms. And then we have a delta that provides some kind of additive slack. And we like our deltas to be very, very small, but think of that as being like cryptographically small. But it effectively says if I have something that occurs with like a probability 0, and then some like very, very small probability under like a neighboring database, that's okay, and that's going to be taken care of by my delta. And so now let's think about this epsilon term. If this epsilon is large, then we're saying this bound actually doesn't hold very tightly if I have a large epsilon, because then like, this term becomes large and this bound isn't particularly meaningful. On the other hand, if I have a very small epsilon, in particular, as this epsilon approaches 0, this term comes close to 1, and these two things have to be close to equal, and so that gives a very tight privacy constraint. And so here having a smaller epsilon means like stronger privacy guarantees. And again, this provides a very strong worst case guarantee because it holds for all databases and for all possible like changing one person's data, and then also for all possible bad things that may happen to you as a result of the analysis. I'm guaranteeing that bad thing is going to happen with about the same probability as it was before, and so we're not having kind of additional harms occur. Good. And so this privacy notion has a couple of very nice algorithmic properties. And the first one is post-processing. And this effectively guarantees no adversary can like break the privacy guarantee. And so things are private once and they're private always. Formally, it says if I have some like epsilon differentially private algorithm, and then you should like also say, because a delta is so small, we kind of often ignore it. And so I may be like, I'm imprecise about the delta, but that's okay for now. I'll be precise where it's important later. And so if I have some like epsilon differentially private algorithm, and I apply like any like function to it, and so think of this as being like an adversary, then the result of the adversary trying to break the private algorithm is still going to maintain the same privacy guarantee. And so this says anything you do to a private output will stay private at the exact same level. And we also have like composition of the privacy guarantees. And this effectively says like that the epsilons are going to kind of like add up as you do additional analyses on the same data. Formally, it says if I have a collection of like a differentially private algorithms, and I want to do them all, and 1 up through nk, where they're each going to be like epsilon I differentially private, then if I do these k different analyses on my data, the result is going to still be like a differentially private. I'm just going to sum up these epsilons. And so this is the kind of like simplest version. We actually have like a stronger composition guarantees. In particular, this one is going to be roughly k times epsilon. We can get that down to like square root k, although there's some constants and some log terms that gets annoying. But like the main point is that we can do multiple private analyses in a row, and like the result is still going to be private. And so like these two things together really give us very nice algorithmic framing, because this says if I want to build a complicated differential private algorithm, all you really have to do is think about simple private building blocks, and then it can just like compose them and post-process them inside of the algorithm. And so this is going to be very nice, and we'll certainly see this throughout the talk, is really what we're doing is we're taking simple private building blocks and we're just like applying them in the right places inside of an algorithm. Good. This is kind of like a wrap-up slide of the like overview. And the main point is that we now have like a whole bunch of like differentially private algorithms for a lot of different problems that you might want to solve: optimizations, statistics, economics, machine learning, you name it. And these things are also being used in practice by some like major like tech firms and also branches of the American government. And one thing that is kind of missing, and it'll be the focus of this talk, is that nearly all differentially private algorithms operate on a static database. And so this says, I'm going to like collect my data once, I'm then going to analyze it as much as I want, publish the results, and I'm done. But if you think about a lot of these use cases by these companies, for example, Google never just like collects all the data once and then analyzes it, but rather it's like a continually analyzing data that it acquires online. And the same thing in virtually every like a DP use case. And so this kind of brings us to the topic that we're going to think about today, which is how to do differential privacy in some kind of online setting. And so if you think about kind of like old-fashioned data science, maybe like in the 90s, how would you get data? Well, companies or governments might like send out a survey in the mail. How was the quality of your service? Rank it on a score of like 1 to 5. Maybe it's a phone survey, but it really was mail out a bunch of surveys, get the results back, and then you analyze it. And that kind of makes sense. But this is not really the world that we live in now, as we have like, smartwatches, social media, routing and GPS. Everything is changing continuously. You can't just like wait until you collect like all the tweets in the world and then analyze it, but instead we have to do like a continuous analysis on a changing database. And like also in terms of these examples, we're going to see like healthcare, social media, physical location. These things require privacy guarantees. And so we both have to do online analysis, and we also have to incorporate formal privacy guarantees. And so this is where like a differential privacy is going to be brought to bear. So I'll pause now if there's any questions before we get into the like a technical part of the talk. Okay, great. So like in this talk, I'm going to go through three different problems where we can apply like a differential privacy to these online learning problems. And I'm going to talk about kind of like a whole bunch of different papers. And so this is why I mentioned this is going to be an overview. We're not going to go very deep into any one paper, but I am very happy if you have any questions afterwards or during to kind of go into more detail. And so the three problems that we'll talk about today is we're first going to ask, how can we extend standard differential privacy results into the growing case? Because we previously didn't even know how to do this. And then we're next going to ask about how can we identify if our data changes over time. And then we'll talk about doing a private online hypothesis testing. And so this is more of a classical statistics problem. So we'll start here. And the general question is going to be, given a private and accurate static algorithm, how can this be used as a subroutine in the dynamic setting? And this is inspired by the fact that we have a whole lot of differential private algorithms that we know perform well, and they provide high quality accuracy, high quality results, and they apply only to a single fixed database. And so rather than saying throw out a decade and a half of research and start fresh, we're going to ask, how can we use all these existing tools and still find value in them as we're in this evolving setting? And so in the easy case, in the kind of ideal case, maybe I will get and new points of data, and then I'll get a bunch of queries, and I can then evaluate these queries on this data. And then the process kind of repeats. And it's obvious if I have a static subroutine, I'm just going to run it at various points. And so certainly I should wait until I get new data and new queries, and then I can just rerun this algorithm, and I can just do that a bunch of times. The problem is that this is not what data growth looks like in practice. I may have very bursty query needs, and I may have very bursty data collection. And the question is then, in this complicated space, when do I run the algorithm? And because we're no longer in such a fixed structured setting, I can't just go with these at these scheduled intervals. So in the context of a differential privacy, there's a notion of query sensitivity, and this is basically the maximum amount the function value can change if you were to change one person's data. And I will denote this delta F, and this is going to be the max over these neighboring databases of just an absolute value change in the function's value. And so this is the kind of maximum, how much can one person's data change the answer. And so for this talk, think about counting queries that are of the form, what fraction of the entries in the database satisfy a certain predicate P? And so this could be, what fraction of the entries are men? What fraction of the entries are more than 5'3"? What fraction of the entries have a heart condition? Things like this. And so then in this case, delta F is going to be 1 over n for a database of size n. And in our case, this n is going to be changing over time. And so that's a part of what makes it tricky. And we'll talk about accuracy with respect to this alpha beta accuracy notion. And so we'll say that some algorithm is going to be alpha beta accurate with respect to a query class F. And so this may include multiple of these queries. If it is a case that for any database X, I'm going to have additive error at most alpha for all of the queries in my class with probability 1 minus beta. And so this alpha is my kind of like additive error, and the beta is my failure probability. And I'm being like a little bit imprecise here, and so it should be like, the function evaluated on the data compared to the function evaluated using like whatever the output of the algorithm is. It might be a database where it makes sense to kind of like, plug this in to the function, or it might be something else and you're going to use this to evaluate the query. And so I'm being like a little bit imprecise here, but this is saying if I were to compare the answer I get after applying the algorithm to the answer I get on the real data, I want that difference to be most alpha. And like the main result of this paper is what we call like a black box scheduler. And this is because it takes in a private accurate algorithm that we're going to treat like a black box. And so we're just saying, I have no idea how this thing works, but I'm just going to treat it as a black box, and I'm going to schedule it to run at various times. And so if our like original algorithm is going to be like alpha prime, beta prime accurate, and it's going to be like epsilon prime 0 differentially private in a static case, we're then going to use that as a black box, and we're going to like schedule times like to run this black box, and these are going to be spaced out at kind of like exponentially spaced intervals. And this will give us a couple guarantees. The first is that we want all of our like epsilon i's to sum up to some fixed finite epsilon. And this will come from like composition. And we also want all of our failure probabilities of these runs to sum up to something finite and hopefully smaller than 1. And this is because we're going to bound everything with a like union bound. And of course, the actual algorithm gives a lot of details in terms of like, how do you optimize these times ti, and that's like the main result. But because I'm doing like an overview, I'll just say that like the result is an epsilon 0 differentially private algorithm, and it's going to be alpha beta accurate, even allowing for like an infinite data growth and only small accuracy loss compared to this like, alpha prime. And this is like exciting, the fact that we can do it across like infinite data growth, because we're saying I'm going to sum up like, infinitely many of these things. And if you don't space those out correctly and tune the epsilon parameters appropriately, you're either going to have your total privacy loss summing to infinity, which is not good, or you're going to have to add so much noise to achieve very small epsilon that you have poor accuracy. And so this is kind of the balance that we're trying to make here, is we're able to get both privacy and accuracy, even in the case of like, infinite data growth and like infinite queries. So let me make this more like concrete, because this is very abstract. And so let me show you how this works in the case of what's called small dB. And this is a paper that came from Blum, Liggett, Roth in like 2008. And so this is a private accurate static algorithm for doing synthetic data generation. And this algorithm takes in a database X of size n, and we have size of our data universe, and we care about answering capital F queries correctly. And this algorithm is then going to output a database Y of size log F over like alpha squared, and this will cause us to have like alpha beta accuracy. And it does this in this very simple way. It basically like samples this y from the space of all databases of this size, and it has like an exponential bias towards ones that provide accurate answers for all possible queries. And so basically, this is going to be our like a black box, yes, and we have this accuracy theorem from the original paper, and so it's private and it's accurate. You don't have to worry about the like details here. The main things that you want to note is you have like some things in logs all over like epsilon n raised to the power 1/3. Yeah. And this power 1/3 is going to be important. Everything else is in logs, and then we have like epsilon n. And so we're now going to apply our like a black box scheduler using like small db as our black box, and we're going to call this small dbg, which is like small db for like growing databases. And how this works is we're going to run small db with these certain parameters, and so this is going to be a time ti. I'm going to run it on my current database. On my query class, I'm going to have an alpha, beta I, epsilon I, and recall these are going to be tuned to make sure that I can sum everything up to something finite. And these are going to be a kind of like exponentially spaced intervals. And so, and this gamma parameter is going to be less than 1. If it were like exactly 1, then it would be like, 2 to some power, but instead it's going to be maybe like 1.5 to some power. And you can tune this, of course. And so it's going to be, and so it is going to be a kind of like exponentially spaced intervals, but it's not, but it's going to have like a smaller base of the exponent than what you are used to. And so we're going to use these to produce an output stream yi. And then I'm going to use that small db that in fact is a database, and I'm going to use that database to just answer every query that arrives. And because these are produced privately, I can then just like directly answer queries on it, and that's also going to be private because of post-processing. And of course, we're going to tune these things as a function of the size of the data set to make sure they sum up to something finite. And the main result here is that our small dbg is again going to be epsilon differentially private, and is also going to be alpha beta accurate. And if we look at the alpha, we still have like things in logs over like epsilon n, but the difference is now we have this like 1/5 power instead of 1/3. And so we have like everything else is kind of like about the same, but our power is now slightly smaller, and so then this like alpha is going to be slightly worse. And so this is what I mean when I say we're going to have roughly the same outcome, slightly changed. Things are still going to be private and accurate with only some like small loss in the accuracy. In the paper, we extend this in a handful of ways. For example, we give an epsilon delta differentially private version of this, and this gives improved accuracy because we do have this like additive slack term at the cost of a slightly weaker privacy guarantee. We also talk about like alpha t beta accuracy, where this alpha t goes to 0 as t grows large. And this actually makes sense if you're used to thinking about things in kind of like a machine learning context, is you're used to saying, as I have more data, I should get better and better accuracy. And so this kind of enables that. And this does improve, and this does give a better accuracy guarantee once the database is like sufficiently large, once it roughly like squares in size. And we show how to apply this to the problem of doing empirical risk minimization, where it also makes sense if you have a larger training sample, you'd expect to have lower like empirical risk. We also do some things beyond the black box setting, and we kind of like peek open inside of this black box. We extend a particular private algorithm. It's kind of a differentially private version of gradient descent to the growing setting, and there we show there's actually no loss in accuracy relative to the static case. And it turns out we really do have to kind of open this black box and tweak some things, and then we get better results. So I'll pause there before changing topics. Any questions on the growing databases stuff? Okay, so I'll now talk about how to kind of identify changes in your data stream. And this was in fact inspired by the previous work, because really what we tune parameters for is we said in the worst case, over data growth, what do you need to do to ensure accuracy and privacy? But then we said, in practice, no one has like a worst case adversarial data growth. And what if you think your data may not change very often? It may change only periodically. You know, it's like if you are like a new company and you take a new advertising approach, then you might see changes. But if you don't see like any changes, maybe you can do better. And so this next topic is about kind of like how do we privately identify when a change has occurred or not. And this is actually about like 3 separate papers, all like on the same topic. So these 3 are going to blend like together in this next part of the talk. And the general question is going to be when can we privately identify when the new data are going to be fundamentally different from the old ones? And this is known in the statistics literature as a change point problem. And the goal is to kind of identify distributional changes in a stream of data. And the model is I'm going to have some points sampled from a pre-change distribution, IAD. And then at some time, K star, they're going to change to being sampled from a different distribution, P1, and I'll call that my like a post-change distribution. And the main challenge is that this change point time, K star, is not known. What do we care about this? For one thing, like disease outbreaks, and it was Ebola, although these days COVID, is we might want to know when do we see like a dramatic change in the like number of cases in a certain place. We may also care about doing this for like a smart home devices. They want to know when is a person's activity level in the home change, because that might mean they're not home and we can turn down the like air conditioner if they aren't home. But of course, in both of these problems and in like other applications, we're talking about highly sensitive data. We're talking about like disease outbreaks. We're talking about like, behavior in the privacy of your own home. And so again, we have to have like privacy guarantees here. And I'll say I will start by talking about the case where these like P0 and P1 are going to be perfectly known. We do relax that in the extensions, but I don't think I talk about it much today. But for this talk, you can like assume that we perfectly know these. Okay, and so this problem has been solved in the non-private case since the 50s. And there's an algorithm. It's known as the like cumulative sum, also known as like a Q-sum algorithm. And it takes in data and it computes this like a generalized log likelihood ratio for every possible point K. And so we're basically asking, is K a change point? How likely is it that K is a change point given the observed data? And then you just output this like maximum likelihood estimator K hat, which is the K that has a largest likelihood. It's very simple. And so then to make this private, we're going to have to either compute LK privately, or we can compute argmax LK privately. And in fact, we're going to compute the argmax privately. And so we're going to use this like a private tool. It's called report noisy max. And this was introduced in the privacy textbook by like Dwork and Roth. It is like inspired by some other things that existed in papers and kind of became folklore, and they were the first ones to actually write it down formally. And so effectively, this approach is going to calculate noisy approximations for a stream of queries, and then report the query that produced the largest noisy value. And so you will note at this kind of like structure is like extremely similar to the like a Q-sum approach. So I'm going to take in a database, queries, and a privacy parameter, and for every possible query, I'm going to first evaluate that query, and I'm then going to sample noise drawn from a like Laplace distribution, which is basically a like a two-sided exponential centered around 0, and so this has mean 0, and its tails decay at like exactly this like exponential rate. It's honestly not a very common distribution, except in like a differential privacy. So if you want, you can think of this as a Gaussian instead, like Gaussian of mean 0. The reason that we don't use a Gaussian, even though they're much more common, is that a Gaussian only gives you epsilon delta privacy, and a Laplace gives you like epsilon 0, but that's the only difference. And so you can like internally think of it as a Gaussian, but it is a slightly different thing. But it still has mean 0. And we're going to tune the parameter, which in this case tunes the variance of the noise, again by like delta fk, and we're also going to include 1 over epsilon. So we're going to like for each of these queries, evaluate the true answer, sample some noise, and we're then going to publish the k hat that has the largest noisy value. Simple. And the idea that we're going to apply for this problem of doing like offline private change point detection is we're going to run report noisy max with this log likelihood ratios as our queries. And that's actually like precisely what this is. And this is our algorithm in the offline case, how we have the entire database up front. Is we're basically doing like QSUM plus report noisy max. And so we're going to like treat these things as our queries, sample noise, and then we're going to like output the K tilde that had the largest noisy log likelihood. And there's one like little assumption here, which is that we need this to be finite and to be reasonably small. This is not true in general. And we relax this in the paper, but for the talk, let's like, think about this as being finite and like reasonably small. And so this is for the offline case. And we're again going to use this as a like subroutine for the online case. Oh, sorry, I forgot. We have an accuracy theorem. So this is private, and we have like alpha beta accuracy for this alpha. We can like interpret this, and this first expression is a non-private accuracy, and this is what comes out of just like a QSUM itself. And this term, if you look at it, is actually like about the same asymptotically. We basically exchange C squared for a C times epsilon, where C is a KL divergence between the pre-change and post-change distribution. And so we see that our cost of privacy asymptotically is roughly like the KL divergence over epsilon, moving between like this term and this term. There's some constants, but it's basically this. For time, let me kind of skip ahead and talk about how to do this in the online case. And so this is more challenging because you have to identify changes quickly without very much post-change data, because the whole point is you want to say, I found a change, I think it occurred yesterday. And that means you don't have very much post-change data if you do this identification quickly. So the high-level approach is we're going to privately detect online when the log likelihood is above a certain threshold on a sliding window of the last n points, and we're then going to run this like offline algorithm on the identified window. And fortunately, we do have like a differential private algorithm for doing this, and this is called like above noisy threshold, and it does exactly what it sounds like. Is it checks when do some query answers exceed a certain threshold, and adds noise to ensure privacy. So it does this. So we take our threshold and we add noise, and we again, like for each query, sample the like Laplace noise, and we then check if the noisy answer is above a noisy threshold. And if the answer is yes, then we're going to halt, and we're going to say like, I found something that is interesting. Otherwise, we're going to continue going. And so this is useful for things like, I have like 1,000 variables and I want to check for pairwise correlation. I think most of them are not correlated, but a small number of them might be. Or you might be doing, I have a lot of like, possible drugs I want to test. And I want to find one that is effective. And so I just have to like, test a bunch of things until I find one that is interesting. And I think that kind of like, most things are not going to be interesting, but I might find one that is. And so that's when this algorithm is like particularly valuable. So the online setting, the plan is going to be to run above noisy threshold on these log likelihood queries, the same way that we did in like QSUM, on a sliding window of the last n points. And then once like above noisy threshold tells us halt, I found a query that is interesting. I found a window where I think a change occurred. We're then going to run like an offline algorithm on that window. And so in pictures, it might be, you know, here, the query is going to have answer below threshold, so nope. Here, it's still below threshold, so nope. And then here, the query answer, which might be the fraction of points that are red, is going to be above a noisy threshold. And so I'm going to raise an alarm, and it will then run like on the offline algorithm on this window, and it will hopefully tell me about here. So that's the plan. And the result is we have an epsilon differentially private algorithm with accuracy loss of order 1 over epsilon compared to the non-private case. And so this means that we match in kind of all the other parameters, but of course we have some loss in terms of the epsilon because we have privacy now and we didn't before. In our follow-up papers, we extend this in kind of multiple ways. The first is thinking about multiple change points. And this is a particularly hard problem from a statistics perspective, is identifying multiple change points. But fortunately, using private tools actually makes this a pretty easy problem to solve. And there's an extension of above threshold that's called sparse vector, and you run this n times. And from our statistical perspective, is we're running basically instantiations of identifying a single change point. And we do have some small accuracy loss in a log term because we do have to take a union bound over the failure probability of these m things, but that's in a log, so it's okay. We also extend to the case where the P0 and P1 are not known. And so I mentioned at the beginning, we're going to assume they are known, but really that's not a particularly practical assumption. And really in practice, an analyst is going to be asking, do I see a difference? Did I see sales increase as a result of my new marketing approach, right? And they're not saying, I think sales are going to be Gaussian with mean 1 and variance 0.5. No, but they're saying, I think the mean is going to be higher. And we can, in fact, extend this framework to this case. We need a new test statistic because our log likelihood queries rely very heavily on these distributional assumptions. And so instead of using that, we use a rank-based test statistic. In particular, we use a Mann-Whitney test, and it basically asks how many of these samples are above these samples. And so you're basically counting and comparing without having to know exact P0 and P1. And we have the same results. So we have epsilon differential private algorithm with accuracy loss 1 over epsilon compared to the non-private case. And then we also extend this to apply to what's known as a drift change, where the points are not sampled IID, but they may be changing slowly over time. So I'll pause here before I move into the final topic of the talk if there's any questions. Okay, so our last topic is going to be private online FDR control. And the main question here is going to be, how can we do online private hypothesis testing without worrying about our p-values blowing up? So as we talk about p-values and hypothesis testing, the framework that we're going to be thinking about is we observe samples x1 up to xn, and we want to test some kind of null hypothesis against an alternative hypothesis. And the null one is a boring one. This is saying like the drug like didn't work. For the alternative one is to say the drug works and we see people being cured of a disease. And the p-value is the likelihood of observing this particular sample under the null. And so if we have a large p-value, then it means our sample is likely under the null, which we can say, I think is likely the null was the true one, and so that is kind of uninteresting. Whereas a small p-value tells you that this sample is very, very unlikely under the null. And so therefore, I think the alternative hypothesis is the one that like generated the data. And so I'm going to reject the null. And so typically we like to, reject the null if p is smaller than like 0.05 or 0.01 or something. And we say, I found like a discovery. I found a drug that works. But this also means, and this means there's less than like a 5% chance of the sample occurring under the null hypothesis, which is great, but there's still a 5% chance because again, this all like probabilistic, and so we can't say for sure that it wasn't the null, but I can say very unlikely. But now what happens if I'm testing many, many hypotheses? For example, if I test 20 hypotheses, an expectation, I expect one false discovery, which is when I think I found a discovery, but the null was true. And if I test 1,000 hypotheses, I expect like 50. If I'm doing genomic testing, I might be testing millions of hypotheses, and I expect a pretty large number of things that are not true. And so we have to control for this. And so this is the problem of doing false discovery rate control. And a procedure for doing FDR control takes in a stream of p-values for all hypotheses, and then decides which ones I want to reject the null. And if you're doing this offline, maybe you want to collect all the p-values and then reject the k hypotheses with the smallest p-value. On the other hand, if you're doing this in some kind of online sense and you have to make decisions immediately, I may want to reject a hypothesis HT if the p-value is smaller than some threshold that I computed beforehand. And these are typically the two types of procedures that you see. And so let's define the metric. So let R be the set of all rejected hypotheses, and let H not be the set of hypotheses for which the null is actually true. And of course, you don't know this, but you can compare. So the FDR rate is a kind of expectation of the number of null hypotheses that are rejected divided by the number of rejections. And so this is basically the fraction of your rejections where the null is true. And so you want this thing to be small, you want it to be close to 0. And so in the offline case, we actually know how to do this both privately and non-privately. And so in this offline case, we're going to know all the p-values in advance, and we're then going to make reject decisions at the end. And so we know how to do this privately. There was a paper in 2018, and the key idea is they're going to use report noisy max that we saw previously to privatize a kind of a best known non-private offline FDR control algorithm, which is known as the Benjamini-Hushberg procedure. And this is of the approach where you kind of take them all and you reject the k smallest ones. And so you're basically going to like continuously, repeatedly do this like report noisy min to make this private. Like in the online case, p-values arrive one by one, and so you can't take the min or take the argmin. And so we actually don't know how to do this privately, or at least like until this work. So we have a lot of non-private work. We have a lot of like non-private tools, and these started with kind of like online alpha investing rules, and then like an extension of that, which basically framed this as an investment problem. And the nice thing is that we're very good at solving like investment problems online. And so we can apply like all of those tools. Basically, like an analyst has some kind of like initial endowment. Every hypothesis they test has a like unit costs, and you get a reward for like our discoveries. And once you frame it in this way, we can apply all of our standard online like investment optimization tools. And a recent extension is the like saffron procedure, and this is considered current state of the art, and it improved performance of the algorithm by kind of adaptively estimating the like a proportion of true nulls. So like we were inspired by the saffron algorithm in name as well as in content, and because saffron is a spice, we also gave our algorithm a like spice name, paprika. And so this stands for like private alpha investing p-value rejecting iterative sparse vector algorithm. And as you see, we had to get a little bit creative with the acronym because we really wanted to dispel paprika, and we couldn't find a K, so we got a little bit creative there. And this is basically saffron plus above noisy threshold we've seen before, although of course there are like a bunch of tweaks, but it's basically at a high level, it is this. So I'll just kind of point out a few of the key things happening here. So we're still going to sample noise, and this is the noise applied to our threshold. And then for each p-value corresponding to our query, if you skip ahead here, we're basically going to sample noise, and then we're going to compare like the noisy version of our query value to the noisy version of our threshold. We have to do a bunch more tricks along the way. So we have our like candidacy indicator, and this is the trick that like Saffron used to kind of adaptively estimate the like a proportion of true nulls, and so this improves performance. And because we are not comparing against a single fixed threshold, we're comparing against our wealth. We then also have to compute the wealth using this like investing rule. And like aside from these, we also have a shift parameter that it turns out to be important in terms of accuracy, but it actually doesn't have as much intuition. But it's basically saffron plus above noisy threshold with a bunch of tweaks. And some important details are that our p-values may be high. So that's why we take logs on both sides, is we allow ourselves to like compute sensitivity a little bit differently. The above noisy threshold accuracy guarantee is not precisely of the form that we want, and so that's what this like a shift parameter does. And we also have this like candidacy condition that we borrow from like Saffron, and it turns out that actually can't be done privately, and so we like relax it slightly, and then we accept a positive delta in our privacy guarantee. And so the main result is that we have an algorithm that is like epsilon delta differentially private, and it controls FDR to be below alpha plus some very small delta t if we want to test t like hypotheses. And so like I'm comparing this to the non-private version is like in the non-private case, we like to control FDR to be below some like fixed alpha, but we have this like additional like a delta t term. So you might be like concerned about that. But recall the very beginning I told you that we like our deltas to be very, very small. Think of them as being like cryptographically small. And so this is actually like an okay term. Even if your t is large, delta t is still going to be very, very small. And we have slightly different technical conditions, whether these p-values are like independent or if they are like correlated. We also have some like experiments, and we show under differing like epsilon guarantees, how does the FDR look? I think in the interest of time, I'll kind of not go through these quickly, but I'll just kind of point out the key observations. We consider both like binomial and like Gaussian data, and we see that our FDR is small. And recall, we like that as being very close to like 0. And we also empirically evaluate power, and we like that being like closer to 1. And we see here that our power is close to 1 if we have a larger epsilon. And like in the Gaussian case, we actually have like very nice power all the way. So this is actually all that I have. I know that it was like an overview, but I also think like the main point I want to convey, if there's any in the audience who are kind of interested in like working on these problems, is there's kind of like two things that are true simultaneously. The first one is that like differential privacy is a very, very well-established field, and it has a lot of tools that can solve a lot of problems. But on the other hand, there's still some like very important open problems, in particular by kind of understanding how do these like theoretical guarantees differ from like the needs of practice. And so this was kind of like an inspiration of this work, is we're saying, yes, we have all these tools and we have all these algorithms, but we can't like, analyze like Twitter streams in real time. That seems important. And so kind of like identifying what are the problems in practice that are not handled by theory. And there's like a ton of those that are still very open and very much need like private versions of these algorithms. And I will end there. Thank you.